This is GCSE Maths grade 9 to 1 higher tier, and we're going to start off with the topic of numbers. Okay, so first thing we need to know is BIDMAS. So BIDMAS tells us the order of operations that we must do. So first we start with B, which is brackets. Then I for indices. So when you have your squares, your cubes, your to the power of 4s. Then division, then multiplication, then addition, and then subtraction. So sometimes you will see that division and multiplication, it doesn't really matter which order you do it, and the same thing goes for addition and subtraction. However, you should always do your brackets and indices first before you do your division, multiplication, addition, or subtraction. Another thing that is very important to know is to remember that when you are multiplying two positive numbers together, you are always going to get a positive. A positive and a negative number, you are always going to get a negative number. But when you multiply two negative numbers together, you get a positive number. Very important. So two positives make a positive, two negatives make a positive. A positive and a negative makes a negative when multiplying. Okay, let's look at these two questions here. So question 1, we have -2, -4 brackets, -5 to the power of 4. So using our BIDMAS, B stands for brackets, so we have to do the brackets first. So brackets is -5, and then indices up, we have an index here, which is 4. So we need to find out what -5 to the power of 4 is. Okay. -5 to the power of 4 is 625. So we've got -2 -4, 625. 625 times by -4, because we'll do multiplication next, is -2,500. And then we do -2 -2,500, which we get as -2,502. Okay, excellent. Question 2. Got 3.7 plus 8.16 times by 4.9. Okay, using our BIDMAS, we have to do multiplication before we do addition. So we do 8.16 times by 4.9. 8.16 times by 4.9 is 39.984. Then we need to do 39.984 add 3.7. Which we get an answer as 43.684. Okay, so let's look at this question here. Beth is choosing between two mobile phone deals. Okay. Determine which deal is better value. So deal 1, initial cost of £97 and £26.82 per month for 2 years. Okay. In 1 year is 12 months. So 2 years would be 24 months. Okay. So essentially what we're going to do here, we're going to do £97, add £26.82 times by 24. And using our bid math, we're going to do the multiplication first before we add. So let's do that one first. So when we times these two together, we get an answer of £643.68. So now we just need to do 97 add 643.68, and we get an answer of £740.68. Okay, now let's look at deal 2. No initial costs, but you pay £20.35 per month for 3 years. Okay, so if a year is equal to 12 months, that means we need to do 12 months times by 3, which we get as 36. So 36 months. So now what we need to do is do £20.35 times by 36, which we get as an answer of £732.60. Okay. Now question says determine which deal is better. Okay. So if in 2 years we have to pay, Beth has to pay £740, whereas in 3 years, in deal 2, Beth pays £732.60. I think we can say that this one is better, that deal 2 is probably a better choice, because in more years she's actually paying less than what she would pay for 2 years. So I'll say deal 2. Okay, so now let's look at rounding. Let's say we have a question like this, which says round 0.257 to 2 decimal places. So the first thing we need to do is essentially to consider the second decimal place. So if we look at 0.257, so this 2 is the first decimal place, the 5 is the second decimal place, and the 7 is the third decimal place. But because the question is asking us to round to 2 decimal places, we are only concerned with the second decimal place, which is 5. Next thing we do is we look at the digit to the right of the number. So we look at the 7, which is to the right of 5. And if the number is 5 or more, we round up by 1. Or if the number is less than 5, we round down. And that essentially means that we keep the second decimal to the number 5 essentially the same if our number to the right of 5 is less than 5. So if we look at this 7 here, 7 is more than 5. So that means that we're going to have to round up. So that 5 at the end will turn into a 6, meaning we get an answer of 0.26. Okay, now we've got some more questions. So let's look at the first one together. Round 7.189 to 1 decimal place. So we look, the first decimal place is this one here. So that's the one that we are going to look at. Next thing we do is we look at the number to the right of the decimal place that we are looking at, which is going to be the 8, which is to the right of this one. We see if 8 is bigger than 5 or less than 5. Well, 8 is more than 5, so that means we are going to have to round up. So that 1 will turn into a 2. So our answer would be 7.2 to 1 decimal place. Next question here. Round 4.678 to 2 decimal place. Same thing. This 7 is going to be the second decimal place here. So that's the one that we are concerned with. Then we look at the number that is to the right of that 7, which is this 8 here. 8 is bigger than 5, so that means we round up, meaning that this 7 at the end will turn into an 8. So we get an answer as 4.68 to 2 decimal place. Next one here is round 0.242 to 2 decimal place. So this 4 is the second decimal place. That's the one that we're concerned with. We look at the number to the right of the 4, which is the 2. As 2 is less than 5, that means we are going to round down, meaning that this 4 will stay as it is. So we get an answer of 0.24 to 2 decimal place. Now this one here, round 8.96 to 1 decimal place. So we look at our first decimal place, which is here, this 9. Look at the number next to it, which is 6. So this one's quite an interesting one here. 6 is more than 5, so that means we round up, meaning that the 9 is going to go up by 1. So because when we go up by 1 for this 9 here, this 9 will turn into the 0. And then that 1, we carry that 1 over here to the 8. So we get an answer of 9.0 to 1 decimal place. So essentially what we've done is we round up, this 9 will turn into a 0, and then we add on to the 1 to the number to the left of that first decimal place. And because we are putting it to 1 decimal place, it is very important to add that 9.0. If you just add 9, you're not putting it to 1 decimal place. So, yeah. Significant figures. To round to a number of significant figures, we follow the usual rules of rounding to a certain decimal place. So very similar to what we've been doing so far. However, the first significant of any number is the first digit, which is not 0. So what I'm saying is that if we had a number of 0.00496, and let's say I ask, okay, which one is the first decimal, the first significant figure, it's not going to be this 0, it's not going to be this 0, it's going to be the first non-zero, which is going to be 4. So 4 in this instance would be the first significant figure, 9 would be the second, and 6 would be the third. The second, third, fourth, and so on and so forth, significant figures follow on after the first if the next digits are zeros or not zeros. So again, if we have 0.004602, so as we said, the 4 is going to be the first, the 9 is going to be the second significant figure, 6 is going to be the third, this 0 will be the fourth, and then the 2 would be the fifth significant figure. So if there's a 0 next to the 4 or after the first significant figure, we count the zeros, but the first significant figure is not going to be a 0. So your first significant figure is going to be a non-zero. It's going to be a number greater than 0, essentially. Okay, now we've got some questions. So first one is round 0.002309 to 3 significant figures. So again, 0.002309, the 2 is the first significant figure, the 3 is the second, and the 0 is the third. Okay, similar to what we do with rounding, we look at the third significant figure, then we look at the number which is to the right, that is next to the significant figure that we are looking at. Then we see whether 9 or the number next to the significant figure is 5 or more, then we round up. If it's less than 5, we round down. Because 9 is more than 5, we round up. So this 0 will go up by 1. So we get an answer of 0.00231 to 3 significant figures. Let's look at this one here. Round 0.0287 to 2 significant figures. So 0.0287. So this 2 is our first significant figure and our 8 is our second. Similar thing, we look at the number to the right of the second significant figure, which is the 7. 7 is more than 5, so we are rounding up, meaning that this 8 will go up by 1, so we get a number of 0.029 to 2 significant figures. Now we've got truncation, which is an alternative to rounding. When you truncate, you essentially cut off digits after the place value you are interested in. So for instance, let's say we have a number of 15.795 2. And the question said for you to truncate to 1 decimal place. Similar thing that we do first with rounding is we look at the first decimal place here, which is 7. But what's different from what is different from rounding with truncation is that when we round, we normally look at the number to the right of it, and then we sort of judge, okay, are we going to round up or are we going to round down? But with truncating, we don't really care what number is next to the decimal place that we are interested in. So this 9 can be a 3, a 2, or whatever. We don't really care. So we essentially cut off these digits here. We don't care. We sort of imagine that it's not there. So when we truncate this to 1 decimal place, we just get 15.7. So let's look at this one here. Truncate 0.0287 to 2 decimal places. So this 2 is the second decimal place. When we truncate, we cut off, so we don't care about the numbers to the right of it. So we get an answer of 0.02. Truncate 2.3678 to 3 decimal places. We look at the third decimal place, which is the 7, and we cut off all the numbers that are to the right next to it. So we get an answer of 2.367. Truncate 14.723 to 1 decimal place. Look at our first decimal place, which is a 7. Don't really care what number is next to it because we're essentially cutting it off. So we get an answer of 14.7. So let's look at this exam question. Calculate the area of the rectangle. So very important to underline and highlight key information in the question, which has a width of 89 centimeters. Okay, that must be important. And a length of 367 centimeters. Give your answer to 3 significant figures. So this question is nice to sort of visualize what we are looking at. It doesn't have to be perfect as I'm drawing right here. So length is 367 centimeters and our width is 89 centimeters. The formula for an area of a rectangle is area is equal to length times by width. So essentially 367 times by 89, which we get an answer of 32,663 centimeters squared. But that's not it, because it says that we must give our answer to 3 significant figures. So let's look. The 3 here is the first significant figure, the 2 is the second, and the 6 is the third. We look at the number to the right of the 6, which is the 6. As 6 is greater than 5, that means we have to round up, meaning that our 6 to the left is our third significant figure, is going to increase by 1. So we get an answer of 32,700 centimeters squared to 3 significant figures. Estimation. So to estimate a value for a calculation, first we need to round all the numbers, which I believe rounding to 1 significant figure works best, if not 2 sometimes. And then we use BIDMAS, so our brackets, indices, division, multiplication, addition, and subtraction to work out the estimated value. So let's look at this example here. Estimate the value of 11 times by 5.7 minus 23.4 all over 0.5. Show all of your workings. Okay, so let's round all of these numbers to one significant figure. So 11 to one significant figure. Yep, so the 1 to the left is our first significant figure. 1 is less than, well, the number next to the 1, which isn't 1, is less than 5, so we're rounding down, essentially. So the one significant figure you get as 10. And 5.7 to one significant figure is 6. 23.4 to one significant figure is 20. And 0.54 to one significant figure is 0.5. Okay. Now we do our big maths. So let's look at the top one first. So the numerator of the fraction. Got 10 times 6 minus 20. Using our big maths up here. Multiplication is higher than subtraction, so we have to do 10 times 6 first, which is 60 before we subtract 20. So 60 subtract 20 is 40, so we do 40 divided by 0.5. Okay, 40 divided by 0.5. If this was a non-calculate, well, is it 40 divided by 0.5? If we know it, essentially that's going to be 80. But if we are not too sure, how I like to think about it is as 40 divided by 0.5, which is a half. And then we go over our rules for fraction when we divide fractions, which is our keep, flip, change. So keep the first fraction the same, flip the second fraction and change the sign. So you do 40 times by 2 over 1, so 40 times by 2, which is 80. So now, what if we have to estimate a square root of a number? So to estimate a square root of a number, we need to first find the two square numbers it lies between, and then decide which of the square numbers it is closer to, then use this to give an estimate. So let's look at this question here. Estimate the value of root 76 to one decimal place. So if we think of our square numbers, so we have 1, 4, and 9, 4 times 4, which is 16, 5 times 5, 25, 6 times 6, 36, 7 times 7, 49, 8 times 8, 64, 9 times 9, which is 81, and 10 times 10, which is 100. Okay, so root 76 we can see is between the squares numbers of 64 and 81. So root 64, root 76 is in the middle there, in between there. Then we have root 81. Root of 64 is 8 and root of 81 is 9. So first of all, we know that it's going to be 8 point something. But now we need to decide a given estimate of what value it's going to be. So then what we do is we look, okay, 76, is that closer to 81 or is that closer to 64? Well, let's see. To get from 76 to 81, we have to add 5. And then to get from 64 to 76, we have to add 12. Well, it looks like that this root 76 is close to the 9 side than to the 8. So that means our estimate is going to be, yeah, as I said, close to the 9 than the 8. So let's give us rough estimates. Let's say, because it's not in the middle, it's not snap bang in the middle, because as we can see here, let's say we get an answer of roughly maybe 8.7. Yeah, 8.7, which is correct. But you can also say 8.8 as well. So essentially it's just essentially just estimating, just figuring out, okay, which side is it closer to in terms of which of the square numbers it's closer to, and then from there we provide a sensible and appropriate estimate for this. So if you said 8.7 or 8.8, that would be correct. Okay, similar question again. So estimate the value of square root of 125 to 2 decimal places. So again, square root of 125 is between square root of 121 and square root of 144. Square root of 121 is 11 and square root of 144 is 12. If we look here, which one is 125 closer to? If we look at 121 and 144, we can see that it's closer to this side than the right hand side. So that means that our number is going to be roughly closer to the 11 side than the 12 side. So using that judgment, we can say that, okay, we can estimate that our estimate for this is going to be roughly 11.2. Yeah. Or you can say 11.1. Either or, you would get the marks for that. Okay, so now we are going to switch on to bounds. Bounds define the range within which a value is expected to lie. The upper bound is the maximum possible value within the range, and the lower bound is a minimum possible value within the range. An error interval essentially shows the range within which the true value is likely to be. For instance, for this one down here, 4.5 and then 5.5. So this 4.5 is essentially the lower bound. This 5.5 is the upper bound. And then this whole thing here is essentially the error interval. So when we talk about error interval, we're just showing the range of values this m can be. So let's look at this one here. 3.7 has been rounded to 1 decimal place. What is the error interval? So what we can do is we can write 3.7 in the middle. And then we work out what 1 decimal place higher than 3.7 is, which is going to be 3.8. and 1 decimal lower than 3.7, which is essentially 3.6. And then to work out our upper and lower bounds, so for our upper bound, we're going to work out what is halfway between 3.7 and 3.8, which is essentially 3.75. And then for our lower bound, we work out what is between 3.7, so the middle number for 3.7 and 3.6, which is going to be 3.65. So this here is our lower bound, and this one up here is our upper bound. So that means that our number has to be bigger than or equal to 3.65. But it has to be less than 3.75. And we have to say there has to be less than 3.75 because if we round 3.75 to 1 decimal place, because the 5 here is 5 or more, that means that we have to round up. So if we rounded 3.75 to 1 decimal place, we'd get 3.8. So that means that our number has to be less than 3.75. And the reason why it has to be equal to or more than 3.65 is because if we round 3.65, the number to the right of this 6 to 1 decimal place is 5. So that means we have to round up. And if we round 3.65 to 1 decimal place, we get 3.7. So that's why we have to say it has to be equal to, it can be equal to 3.65. Okay, this one here, 3.7 has been truncated. Very important. Truncated means cut off. Well, how I like to see it as cut off anyway, to 1 decimal place. What is the error interval? So, remember that truncate essentially means cut off, or how we know it as. So, if we use the idea of it being cut off, that means that our value, so our range of values for this to be truncated to 3.7 to 1 decimal place means that our number can be 3.7, but it has to be less than 3.8. So we have to write this sort of interval here. And the reason why it has to be less than 3.8 is because if we truncate 3.8 to 1 decimal place, we get 3.8. But if we have a number of 3.7999999, it doesn't matter what number is next to the 7, because we are only interested in the first decimal place, which is 7. When we truncate, we cut off, so we don't care what number is next to the 7. It can be 9s, it can be 6s, it can be 3s, it can be 2s. We essentially just cut it off. So essentially 3.799999999 is going to be 3.7 when truncated to 1 decimal place. So that's why we say our interval has to be equal to or more than 3.7, but it cannot get to 3.8, because if we truncate 3.8 to 1 decimal place, we get 3.8, but we want to get 3.7. Okay, so this is an exam question, well, and sort of exam style question. So the mass of an apple A in grams is given as 80 grams. Give the error interval for A in each of these situations. So part A, when the mass was rounded to the nearest 10 grams. Part B, the mass has been, was rounded to the nearest integer. Or part C, the mass was truncated to an integer. That is meant to say was, not been. Yeah. Okay. So let's look at part A. So first thing we do, highlight important key bits in the question. So yeah, mass of an apple, okay. Error interval, yeah, using A, so our A is going to be in the middle of our error interval. And it's rounded to the nearest 10 grams. So we can do our number line. So 80 grams in the middle. We work out what is 10 grams higher than 80 grams, which is 90 grams, and 10 grams less than 80 grams, which is 70 grams. So for the upper bound, we have to work out what is halfway in between 80 grams and 90 grams, which is going to be 85 grams, which is our upper bound. And then for a lower bound, we work out what's between 70 grams and 80 grams, like smack bang in the middle, which is going to be 75 grams. That is our lower bound. So, therefore, in error intervals, our number has to be, to the nearest 10 grams, has to be equal to or more than 75 grams. So A, but it has to be less than 85 grams. Okay, part B. So the mass was rounded, need to get rid of that, to the nearest integer. Okay, very important, nearest integer. Same thing that we've been doing, 80 grams in the middle. To the nearest integer means to the nearest whole number, so essentially the nearest one whole number. So one whole number higher than 80 is 81 grams, and one whole number less than 80 is 79 grams. To work our upper bound, we work out what is halfway in between here, which is going to be 80.5 grams. That's our upper bound. Then for our lower bound, we work out what is between 79 grams and 80 grams in the middle, which is 79.5 grams. That is our lower bound. Then our error interval, we're going to write 79.5. Yep, so A has to be greater than or equal to 79.5, but it has to be less than 80.5 if it has been rounded to the nearest integer. Okay, part C. So the mass of an apple A is given as, 80 grams, and now it's been truncated to an integer. Okay, so when we hear the word truncated, cut off. So first of all, we know that the lowest possible number it can be when truncated to the nearest integer, which means whole number, is 1. Well, 80. 80 grams is the lowest it can be. And then for it to be truncated to the nearest integer, to a whole number, one whole number higher than 80 is 81 grams. So that means that our A has to be equal or greater than 80, but it has to be less than 81 grams when we are talking about truncation. Okay, now we have another exam style question. So it says, consider the formula A is equal to F over M. F is equal to 45 to two significant figures. M is equal to 16.1 to three significant figures. Okay. By considering bounds, work out the value of A to a suitable degree of accuracy. Okay, that's very important. So let's do it. So let's work out the error intervals for F and for M. So let's look at F first. If 45 has been rounded to two significant figures, so essentially here, yeah, 45 to two significant figures, then that means that our error interval has to be between 44.5 and 45.5. Because if we round 44.5 to two significant figures, we get 45. Or if we round 45.5 to two significant figures, we get 46, meaning that our number for F has to be less than that. Now let's look at M. So M, our 16.1, has been rounded to three significant figures. So 16.1 to three significant figures. So that means our lower bound is going to be 16.05 and our upper bound is going to be 16.15. Okay. So now we need to work out our upper and lower bounds for A. So A is equal to F over M. So when dividing, it's important to remember that to find the upper bound for A, we have to use the upper bound for F, divide by the lower bound for M. Because let's think about it. If we have like 100 divided by 2, so 100 over 2, for instance, gives a big number, right? Gives 50, which is a big number. If we do 100 divided by 50, so same big number divided by, let's say, a big number, we get a really small number. So if we do a big number at the top and we divide by the smallest number possible, get a big number. If we do a small number at the top, divide by the biggest number that we can find, we get a small number here. So for our upper bound for A, we are going to do our upper bound for F, which is 45.5, divide by our lower bound for M, which is this one here, 16.05. And then for our lower bound for A, we're going to do the lower bound for F, so 44.5, divide by our upper bound for M, which is 16.15. Okay, so let's look at the upper bounds. If we do that onto our calculator, we should get an answer of 2.834, so on and so forth. Then for our lower bound for A, we should get an answer of 2.755. Okay, so we've done the big bulk of the question. So now we need to do the last bit of the question, which is to find a suitable degree of accuracy. So what that essentially means is we look at the upper bound for A and the lower bound for A, and we try to round each of them to 1 significant figure, 2 significant figure, 3 significant figure, so on and so forth, to see where the upper bound and the lower bound match. And the more significant figures it is, the more accurate our answer is. So let's look at the upper bound for A. If we round the upper bound for A to 1 significant figure, so upper bound to 1 significant figure, we get an answer of 3. Let's look at the lower bound. Lower bound for A to 1 significant figure, we also get an answer of 3. Okay, can we try to make it more accurate by maybe doing 2 significant figures? So if we look at the upper bound for A, let's say to 2 significant figures, we get an answer of 2.8. And if we look at the lower bound for A to 2 significant figures, we get an answer of 2.8 as well. Okay, that's looking a bit more accurate. Let's see if we can round to 3 significant figures. So if we round the upper bound for A to 3 significant figures, we get an answer of 2.83. Whereas if we round our lower bound to 3 significant figures, we get an answer of 2.76. Do those two match? Do the upper bound and lower bound match? Are they the same? No, because our upper bound to 3 significant figures is 2.83, whereas our lower bound for A to 3 significant figures is very different, which is 2.76. So that means that our answer, our final answer, is going to be 2.8 to 2 significant figures, as that is where the upper and lower bound for A both match. So 2.8 is our final answer. Okay, let's look at this one here. Another exam question, exam style question. So a rectangle has a length of 18.8 centimeters and a width of 9.29 centimeters, and are each rounded to 3 significant figures. Okay, that's important. By considering bounds, work out the area, so area, important, of the rectangle to a suitable degree of accuracy, and give a reason for your answer. Okay, let's do it. So, area of a rectangle is length times by width. Let's just write that one first down. But what we need to do, as always, as this is a bounds question, is we need to work out our upper and lower bounds for our length and our width. So let's look at length first. We are told that the length is 18.8 centimeters, and they've all been rounded to 3 significant figures, meaning that our lower bound of 18.5 to 3 significant figures is going to be 18.45, and our upper bound is going to be 18.55. So I'm going to write the error interval as this. Same thing for width. So we've got 9.29 being rounded to 3 significant figures. So our lower bound is going to be 9.285. And our upper bound is going to be 9.295. Okay, so as we mentioned, area is equal to length times by width. So to work out our upper bound for area, essentially to work out the highest possible value for our area, we need to times by the highest, by the upper bound of the length, times by the upper bound of the width. So we're going to do 18.55 times by 9.295. And in lower bound, same thing. We're going to do, well, for A, for area, it's going to be 9.285, the width, should have been the length first, but the width times by 18.45. Okay, if we whack that into our calculators, so our upper bound for area, so 18.55 times by 9.295, we should get an answer of 172.4225. And then for our lower bound, we should get an answer of 171.30825. And of course, area is centimeters squared for units. Okay, so we've done the bulk of the question. Now we need to put it to a suitable degree of accuracy. So this bit here. So again, as I said, essentially what we're going to do is we're going to round both the upper bound and lower bound, and we're going to see where it matches. The higher the number of significant figures, the more accurate it is. So let's round, let's say, the upper and lower bound to 1 significant figure. We round the upper bound to 1 significant figure, we get an answer of 200. Lower bound, we also get 200. Okay, they match, but can we do better? So let's look to 2 significant figures. If we round the upper bound to 2 significant figures, we get an answer of 170. And if we round the lower bound to 2 significant figures, we get an answer of 170. Okay, they match, but can we do better? So let's look to 3 significant figures. 172.42225 to 3 significant figures is going to be 172 for the upper bound. For the lower bound, we're going to get 171. Okay, so they don't match to 3 significant figures. So our most accurate degree of accuracy for this question here is going to be to 2 significant figures, as they both round to 170. So we just say 170 centimeters squared to 2 significant figures. And then we can just say as both upper bound and lower bound round to 170 to 2 significant figures. Excellent. So now we're going to look into adding and subtracting fractions. So first, when we are adding and subtracting fractions, we find the lowest common multiple of the denominators. Then we scale each fraction so they both have the lowest common multiple as the denominators. Then we add or subtract the numerators, and we do not change the denominators at all. So let's look at this question here. A jug contains 7/8 liters of lemonade and is left in the jug after 1/6 liter is poured out. Okay, so essentially for this question here, we are going to be doing subtraction. So we've got 7/8, so it contains 7/8 of a litre of lemonade, and 1 litre of the lemonade is being poured out, and we need to work out how much is left. We're going to do 7/8 minus 1/6. When we subtract or add fractions, we need to make sure that the denominators are the same. The denominators here are not the same, so we need to work out the lowest common multiple of 6 and 8, which is going to be 24. Because 24 is in the 6 times tables and 24 is also in the 8 times tables. So we need to convert these two fractions into over 24. So to get from 8 to 24, we have to times by 3. So we do the same thing to the top. Whether you do to the bottom, you do to the top. So if we times the bottom by 3, we have to times the top by 3, which we get as 21. To get from 6 to 24, we have to times by 4. Whether we do to the bottom, we do to the top. So we have to times the top by 4 as well to get 4 over 24. Now that the denominators are the same, which is 24, all we need to do is to subtract the numerators. So we do 21 subtract 4, which is 17. So our answer is 17 over 24 litre of lemonade is left. In the jug. Another one here, 2 pipes of length 2 3/4 meters and 1 2/3 meters are joined end to end. Okay, these two are important. How long is a new piece of pipe? Give your answer as a mixed number. So for this question here, we are going to be doing addition, not subtraction. So 2 3/4 add 1 2/3. So what we do here, these two are in mixed numbers, so we have to convert them into improper fractions. So to convert to improper fractions, what we do is we do the denominator times by the big number here, so 4 times by 2, which is 8, and then we add 3, which is 11. So the 11 will go to the top, so it'll be 11 over 4. Same thing with this one, so 1 2/3, we do the denominator times by the big number, so 3 times by 1, which is 3. Then we add 2 to get 5. Okay. So 11 over 4 plus 5 over 3. Now, as both of the denominators here are different, we have to find the lowest common multiple of both of them, which is going to be 12. as 12 is in the 4 and 3 times tables. So to get from 4 to 12, we have to times by 3. So we times the numerator by 3 as well. 11 times 3 is 33. To get from 3 to 12, we times by 4, so we have to do 5 times by 4, which is 20. As the denominators are the same, we just need to add the numerator together, which we get as 53 over 12. So, to convert from an improper fraction to a mixed number, which the question is asking for us to do, we need to work out how many whole 12s go into 53. So we have to go our 12 times tables, which is 4. 4 times 12 is 48. 53 subtract 48 is 5, so that's our remainder, so our 5 is going to go up there. So our answer is 4 and 5/12 meters. Okay. When we multiply fractions, we multiply the numerators and multiply the denominators together. Sometimes we may cancel down before multiplying the numerators and multiplying the denominators. So let's look at this one here. We've got 8/15 times by 5/12. So what we could do is essentially do 15 times by 12 and 8 times by 5. But what we can do before we do that is cancel down. So when we cancel down, we look at the numbers that are diagonally across from each other. So essentially the 12 and the 8, which are diagonally across of each other, that's one group. And then the 15 and the 5 is another group. And we see whether we can cancel them out. So let's look at the 15 and 5. 15 and 5 are both divisible by 5. So 5 divided by 5 is 1, and 15 divided by 5 is 3. 8 and 12, they are both divisible by 4. So 8 divided by 4 is 2, and 12 divided by 4 is 3. So now we just need to do 2 times 1, which is 2, and 3 times 3, which is 9. Is that simplified? Yes, it is. And that's it. Okay, so let's look at this one. So first of all, we need to turn this mixed number into an improper fraction. So to do that, we do 2 times by 9, which is 18. And then we do 18 plus 7, which is 25. So 25 over 9 times by 3 over 10. And then what we can do is cross cancel out. So 25 and 10, they are both divisible by 5. And then the 3 and 9 are both divisible by 3. So we do 5 times by 1, which is 5, and 3 times by 2, which is 6. And that is it. So now we're going to look at dividing fractions. When we divide fractions, we use the KFC method, which stands for keep, flip, change. So we keep the first fraction the same, flip the second fraction, and then change the sign from division to multiplication. So let's put that into practice. So we have 3/8 divide by 7/10. So if we use our keep, flip, change, we keep the first fraction the same, so 3/8 stay the same. We flip the second fraction, essentially that means the 7 will go down here, and then the 10 will go up there. So we get 10/7. And then we see, which is for change, so we change from division to multiplication. So we do 3 times 10, which is 30, and then 8 times 7, which is 56. We can simplify this as both of them are divisible by 2. 30 divided by 2 is 15, and 56 divided by 2 is 28, like so. Let's look at this one here. So we've got two mixed numbers. So as always, we have to convert the mixed numbers into improper fractions. So let's look at 2 and 2/5. 2 times by 5 is 10, add 2 is 12. 5 3/4. 5 times 4 is 20, add 3 is 23. Okay. Keep, flip, change. Keep the first fraction the same. Flip the second fraction, and then change the sign from division to multiplication. So we do 4 times 12, which is 48, and 5 times by 23, which is 115. Now we're going to look at fractions, decimals, and percentages. So this table here shows you a list of tables that, well, list of fractions, decimals, and percentages that you should know off the top of your head. So a half is 0.5, 50, which is 50%, a quarter is 0.25, which is 25%, an eighth is 0.125, which is 12.5%, a third is 0.3 recurring, which is 33.3 recurring percent, a fifth is 0.2, which is 20%, and a tenth is 0.1, which is 10%. These are the stuff that you just need to know off the bat from the top of your head. Now we're going to look at converting. So when we want to convert from a fraction to a decimal, we divide the numerator by the denominator. So for instance, we can say 32 over 100. So when we want to convert from a fraction to a decimal, we are essentially doing 32 divide by 100. And whenever we divide by 100, if we remember, so 30 is the same thing as 32.0. When we divide by a multiple of 10, we move the decimal place to the left. So because there are 2 zeros, we move the decimal place 2 times to the left, like so. So we get an answer of 0.32. Then when we want to convert from a decimal to a percentage, we times by 100. So we do our 0.32 times by 100. When we times by a multiple of 10, we move the decimal place to the right. So because there's 2 zeros, we move it 2 times to the right. So we get 32%. And then from a percentage to a fraction, we divide by 100. So 32 over 100. Remember, in a fraction, that 9 means divide. Okay, this question here, write the fraction 5 over 16 as a percentage. So to convert from a fraction to a percentage, let's convert from a fraction to a decimal first. So when we convert a fraction to a decimal, we divide the numerator by the denominator. So if we do our bus stop method, 16 from the outside, we have 5, I'm going to put 0.0000. So we can't do 5 divided by 16, so put a 0, put our decimal place, and we carry that 5 along. How many 16s go into 50 is 3, and that remains 2, because 3 times 16 is 48. 50 subtract 48 is 2, so that's where we get our 2 from. How many 16s go into 20 is 1, and that remains 4. How many 16s go into 40, and that is 2. 2 times 16 is 32, and that remains 8. How many 16s go into 80? Oh, that one is 5. So we get an answer of 0.3125. Then when we want to convert from a decimal to a percentage, we times by 100. So when we want to times by 100, we are moving the decimal place 2 times because we've got 2 zeros. So 1 and then 2. So our decimal place is here. So we get an answer of 31.25%. To know whether a fraction is a recurring or terminating decimal, so recurring is like that 1/3 where you have that dot above the 3, that's a recurring. A terminating decimal is like 0.5 when it's not continuous, like it's no continuous number, because you've just got 0.5, which is a half. So to know whether a fraction is a recurring or terminating decimal, we simplify the fraction fully and find the prime factors of the denominators. Prime numbers are numbers that are only divisible by itself and 1, such as 2, such as 5, such as 3. And if there are any prime factors other than 2 or 5, then the decimal will be recurring. So let's put that into practice. So we've got show that the fraction 21 over 98 is a recurring decimal. So 21 over 98. First thing we need to do is to simplify fully. Both 21 and 98 are both divisible by 7. So if we divide 21 by 7 and 98 by 7, the top we get as 3, and on the bottom we get as 14. Then what we do is we find the prime factors of 14. So prime factors of 14 is 7 and 2. And because we have another prime factor other than 2, which is 7, that tells us that 3 over 14 is going to be a recurring decimal. So as we have prime factor 7, this is a recurring decimal. And just to prove my point, if we put 3 over 14 in our calculators and we turn it into a decimal, yep, we do get a recurring decimal. So we are correct. So now let's look at recurring decimals. So recurring decimals are decimals in which one or more digits repeat infinitively. So it's ongoing. For instance, 0.3 recurring, that dot there essentially means that it's 0.333333, and it goes on pretty much forever. So let's look at this question here, which says write 0.72 recurring as a fraction. So what we do here is we label 0.72 as x. So let x equal to 0.72727272 dot. And then we find out what 10x is. Remember, whenever we times by a multiple of 10, we move the decimal place to the right. Because we are timesing by 10, we move it once to the right. So we get an answer of 7.27272727. Okay, essentially what we are trying to do is essentially try to subtract the numbers from each other and get rid of the sort of decimal point, so the numbers after the decimal point. So if we look at x and 10x, we can see that if we subtract x from 10x, we're not eliminating the numbers that are next to the decimal point, are we? So let's look at 100x. So if we times 0.72 recurring by 100, we get 72.727272. So now we can see that the 100x, and the x next to the decimal point, so the 727272 and the 727272 for x and 100x match. So when we subtract them away from each other, we can eliminate the numbers that are to the right of the decimal point. So if we do 100x, subtract x, same thing as saying 72.7272 and 0.7272. If we subtract that, this side we get a 72. 100x take away 1x is 99x. So if we want to make x the subject here, essentially what we need to do is divide by 99. So x is equal to 72 over 99. Now, as this question doesn't tell us to simplify, we can leave it as it is. But if the question said that we must simplify to its fullest, then if we can see, both of these numbers here are both divisible by 9. So if we divide 72 by 9, we get 8. And if we divide 99 by 9, we get 11. Okay, so now we're going to look at surds. So surds is an irrational square root such as square root of 3, or square root of 5, or square root of 7, and so on and so forth. So for instance, square root of 4 is not an irrational number because the square root of 4 is 2, or technically plus or minus 2. Okay, so when it comes to surds, there are a few rules you need to know. First of all, when you have square root A times by square root B, essentially you're doing the square root of A times by B. So let's do an example. Square root 2 times by square root of 3 is the same thing as saying 2 times 3, but all under the square root, which we get as square root 6. Similar thing when dividing, so if you have square root 8 divided by square root 2, it's the same thing as saying 8 divided by 2 all over square root. 8 divided by 2 is square root 4, and square root of 4 is 2. However, remember that if you have root A plus root B, you just keep it as it is. So for instance, if you have root 2 plus root 3, that is it simplified. You can't simplify it any further. Then if you have brackets A plus root B bracket squared, remember you have your double brackets, and then you would normally do the same method that you would do when expanding double brackets, your FOIL method or your multiplication table method. And once you expand it out, you would get an answer of A squared plus 2A root B plus B. Similar thing when you have brackets A plus root B in one bracket and then A minus root B in another bracket. When you expand your brackets out, you would get A squared plus root B minus A squared plus A root B minus A root B minus B. And these two, a positive A root B and minus A root B, will cancel out each other. So it will always simplify to A squared minus B. There is something that we need to know, which is something called rationalising surds. So when we rationalise surds, that essentially means that we get rid of the surds on the bottom of the fraction, also known as the denominator here. So A over root B, if we were to rationalise the surds, we'd have to times the top and bottom by root B, so that we can get rid of this root B surd here. A root times by itself makes the number inside itself, which is B. So we have essentially rationalized. So for instance, let's say we have 4 over root 7. If we want to rationalize this surd, we essentially have to times root 7 by itself. So root 7 times by root 7 is 7, and then 4 times root 7 is 4 root 7. So that is it rationalized. Sometimes maybe we may get it in this sort of format here. So our denominator is maybe A plus root B, or our denominator may be A minus root B. However, when we want to rationalize, we rationalize by the opposite sign. So for this instance at the top here, we have to times A plus root B by A minus root B, because if we expand out those two brackets, we get A squared minus B, essentially. So let's do an example. So let's say we have 3 over 2 plus root 5. If we want to rationalize this surds, we have to essentially times by 2 minus root 5 for the top and bottom. Okay, so if we do 2 plus root 5 and we expand that one out, and 2 minus root 5. If we use our FOIL methods, so first we would do 2 times 2, which is 4. Outside is 2 times minus root 5, so minus 2 root 5. Inside, so root 5 times by 2, which is positive 2 root 5. And then last, root 5 times by negative root 5, which is 5. The minus 2 root 5 and the positive 2 root 5 will essentially cancel out each other. So these two cancel out. So essentially all we are doing is 4 minus 5. which is minus 1. So minus 1 at the bottom, and then 3 times by 2 minus root 5, which we get as 6 minus 3 root 5 over minus 1, which is the same thing as saying minus 6 plus 3 root 5. Okay, now we've got some exam questions to go over, so let's do them. So this one here, we have to express this in the form of a plus b root b. So whenever you have a question that is in this sort of format here, so a plus b root 2 from this fraction to the left here, that means we are going to be doing some rationalizing. So 1 plus root 8 over 1 minus root 2. So if we look at this root 8 in particular, we can essentially simplify this root 8, because root 8 is the same thing as saying root 4 times by root 2, right? Square root of 4 is 2, so root 8 is the same thing as saying 2 root 2. So let's change that into that. So 1 plus 2 root 2 over 1 minus root 2. And when we rationalize surds, so when we have it in this format, 1 minus root 2, we have to times the top and bottom by 1 plus root 2. 1 plus root 2. Okay, so using our methods that we use, so that means that we get a squared, so 1 squared minus b, so 1 minus 2. Essentially, if we expand the brackets here, I've essentially just done a shortcut method to it, because whenever you times it by the opposite sign, you always get the a squared minus b, where our a is 1 and our b is 2 in this instance. And then if we do the top one, so we're going to have to expand those two brackets here. So 1 plus root 2. Again, we can use our FOIL method. So first, 1 times 1, which is 1. Outside, 1 times root 2, which is root 2. Inside, so 2 root 2 times by 1, which is 2 root 2. And last, 2 root 2 times by root 2. So root 2 times by root 2 is, so think about it as 2 times by root 2 times by root 2. Root 2 times by root 2 is 2, so we're going to do 2 times 2, which is 4. And then 1 minus 2 is minus 1. Okay, so let's simplify this. So 1 plus 4 is 5. Root 2 add 2 root 2 is 3 root 2. And it's going to be over minus 1. When we divide by minus 1, the signs will change. So this will be minus 5 minus 3 root 2. And that is it. Okay, now we have this one. Simplify fully root 45 minus root 32 plus root 5. So whenever we want to simplify surds, it is very important for us to remember our square numbers. So let's go from 1 to 10. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and 10 squared is 100. Okay. And then you have 121, which is 11 squared, and 144, which is 12 squared. Okay. So when we want to simplify a surd, so root 45, we look at our square numbers and see, okay, is there any square number here that we can divide divisible by 45? 45 is in the 9 times table, so we can do square root of 9 times by square root of 5, because 9 times 5 is 45. Square root of 9 is 3, so essentially root 45 will turn into 3 root 5. Same thing for root 32. If we look, 4, yep, matches because 32 is in the 4 times tables. So root 4 times by root 8. Oh, actually, we could potentially do root 16 because 16 is in, well, 32 is in the 16 times tables. So, yeah, let's do root 16. So root 16 times by root 2 makes root 32. Square root of 16 is 4, so it'll be 4 root 2. And root 5 just stays as it is because you can't simplify that. So now we've got 3 root 5 minus 4 root 2 plus root 5. So we can only simplify the root 5 and the 3 root 5. So if we do 3 root 5 add 5 root 5, we get 4 root 5. So this will simplify to 4 root 5 minus 4 root 2. And that is it. Okay, now got another question, so another simplify fully. So let's do it. So root 98, again, we can write, actually, yeah, let's write out our square numbers again. So we've got 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. Okay, off the bat, let's look at root 98. 49, yep, 98 is in the 49 times tables. So square root of 98 is the same thing as saying square root of 49 times by square root of 2. Square root of 49 is 7, so 7 root 2. Square root of 50, yeah. 50 is in the 25 times tables, so it's the same thing as saying square root of 25 times by square root of 2, which is 5 root 2. So now we're essentially doing 7 root 2 subtract 5 root 2, which we get as 2 root 2. Beautiful. Now let's look at indices. So again, similar with surds, there are also some rules that you need to remember when it comes to index law. So first thing is if you multiply numbers with the same base, you add the powers. So here we have 9 to the power of 5 times by 9 to the power of 7. Because they have the same base, which is the 9, you just add the powers. So 5 add 7, which is 12. Similar thing with dividing. If you have numbers of the same base, you subtract the powers. And then when you have your brackets, so here you have 9 to the power of 5 in brackets, and then you have to the power of 4 on the outside. So we call that as raising a power to another. So essentially, whenever you see the brackets, you multiply the powers together. So you do 5 times 4, which is 20. Whenever you do any number to the power of 0, you're always going to get 1. Doesn't matter if it's 9, 7, 16, 400, 5,000, 6,000. As long as it's to the power of 0, you're always going to get 1. A power to negative 1 gives a reciprocal. Reciprocal means you essentially flip. So 9 to the power of negative 1 is essentially 1/9. Because when you flip, when you do the reciprocal, 9 is the same thing as saying 9 over 1. And when you flip, 9 goes down here and the 1 goes up there. So that's how we get 1 over 9. And when we have a power of 1 over n, that gives the nth root. So for instance here, 81 to the power of a half is the same thing as saying square root of 81, which is 9. If you do it to the power of a third, that's going to be a cube root. To the power of a fourth, that is going to be fourth root, and so on and so forth. So now let's look at some exam questions. So here we've got write 8 to the power of 6 divide by 8 to the power of minus 9. Okay, so let's look at the inside first. So 8 to the power of 6 divided by 8 to the power of minus 9. The index law says that when we have powers of the same base and we are dividing, we have to subtract the powers. So essentially what we're doing is 8 here, and we're doing 6 minus 9. Remember, two negative numbers make a positive, so this negative and negative will actually turn into a plus. So we're going to do 8, 6 plus 9. 6 plus 9 is 15, so it'll be 8 to the power of 15. But hold on a second, we're not done because we've got this square root. Square root in powers is a half. So essentially we have something like this. When we see the brackets, we are raising a power to another, so that means we multiply the powers together. So we do 15 times by half, which is just the same thing as saying 15 over 2. So our answer in index form is going to be 15 over 2. Okay, now let's look at this one here. So it says find the value of 64 to the power of minus 5 over 6. So what I like to do when we have something like this, well, first let's write it out. So 64 minus 5 over 6. I like to split this minus 5/6 into a fractional power, so the 1 over 6, and then to the power 5, and then to the minus 1. So what I'm saying is I will split this into 64, then I do the fractional power first, times, and then the number, so the power, the 5, and then the minus 1. So let's do it. So 1/6 essentially means we have to find the 6th root of 64. 6th root of 64, I believe, is 2. Yep, 6th root of 64 is 2. So now that we've got that one done, we now work out what 2 to the power of 5 is. 2 to the power of 5 is 32. And then once we work that one out, we need to do to the negative 1. So we're going to do 32 to the power of negative 1. When we do a power to a negative 1, we do the reciprocal, so we flip, meaning that this 32 will turn into 1 over 32. Okay, now we have something called prime factor decomposition. So prime factor decomposition is the process of breaking down a number into its prime factors. So one of the ways that we show this is doing the tree method. So when we have a number, let's say n, and then we sort of split it into two numbers. And then prime factors are prime numbers that multiply together to give the original number. So prime numbers are numbers that are only divisible by itself and 1. So let's look at this example here. Write 189 as a product of its prime. So what we do here, we write 189 and we split it into 2. So off the bat, we can divide 189 by 3, potentially. So if we do 189 divided by 3, we get 63. And every time we get a prime number, we circle it. Okay, 63, let's think. I believe 63 is also divisible by 3 as well. 63 divided by 3 is 21. So we split down to 3 and 21. And because 3 is a prime number, we circle that as well. 21, yep, we can split that down into 3 and 7. And as 3 and 7 are prime numbers, we circle them as well. So 189 simplifies to 4 as a product of its prime factors as 3 times 3 times 3 times 7. 3 times 3 times 3 is the same thing as saying 3 cubes times by 7. Okay, we've got this one here, 420. 420, let's split that one down. 420, yeah, we can divide by 10 potentially. So 10 and 42. Okay, they're not prime numbers, so we may have to split both of them further down. So 10, we can do 2 and 5. 2 and 5 are prime numbers, so that one is done and dusted. 42, 7 goes into 42. Yep, it does. So 7 and then 6. 6 is not a prime number, but 6 splits down into 2 and 3. Okay, so now we've got 2 times 2 times 3 times 5 times 7. How many 2's? 1, 2. Yep, 3. Yep, 5 and 7. 2 times 2 is 2 squared, so 2 squared times by 3 times by 5 times by 7 are its prime factors. Okay, highest common factor. So the HCF, or highest common factor, is the largest number that divides exactly into 2 or more numbers. Lowest common factor, also known as the LCM, so you may see as LCM, is the smallest number that is a multiple of 2 or more numbers. So, if a question says, for instance, find the lowest common factors and the highest common, the highest common factor and the lowest common multiple of 180 and 84. So what we would do is find our prime factors for both these numbers. So using our factor tree, so 180 goes into 3. So we have 3 and then 60. 60 goes into 3 again. So 3 and then 20. Then you have 5 and 4. Then you have 2 and 2. 84, you have 7, I believe. Yeah, 84 goes into 7. Or does it? Yeah, it does. It does, yeah. So 7 and 12, and that splits into 3 and 4, and that's 2 and 2. Okay. So 180, so 180 is equal to how many 2's? So 2 squared times by 3 squared times by 5. And 84 is 2 squared times by 3 times by 7. Okay, so what we're going to do here is we're going to draw a Venn diagram. So we're going to use the Venn diagram methods to work this one out. So 2 circles. Yeah, this is going to be the prime factors of 180 and the prime factors of 84. So we look at what they have in common. Well, they have 2 2's, so 2 2, and they have 1 3 in common, both of them. However, what 180 only has, 180 has an extra 3 and a 5, and 84 has an extra 7. Okay, so using our Venn diagram method, the highest common factor is going to be the numbers that overlap, that are in the overlap between the 2 circles. So what they have in common, which is going to be 2 times by 2 times by 3. 2 times by 2 times by 3. So 4 times by 3, which is 12. Okay. And then the lowest common multiple is essentially everything in the Venn diagram times together. So we're going to do 3 times by 5 times by 2 times by 2 times by 3 times by 7. Which we get as 1,260. Yep, 1,260 divided. Yeah. So our highest common factor is 12 and our lowest common multiple is 1,260. Same thing for this one here. So find the highest common factor and lowest common multiple of 150 and 60. So 150, we split that one down. So we've got it's divisible by 5 and 30, I believe. Yeah. And then we can also split that down into 5 and 6. And then split that down into 2 and 3. 60, we can also split that down into 5 and 12. 3 and 4. And then 2 and 2. Then we draw our Venn diagram. So 150 and 60. So 150 is equal to, so 2 times by 5 times by 5 times by 3. 60 is equal to 2 times by 2 times by 5 times by 3. Yep. What they have in common, so they both have at least 1 2 and 1 5 and 1 3. What 150 has is they have an extra 5, and they believe that is it. So 5 5 2 3. 60 has an extra 2. Yeah. Okay. So then the highest common factor is going to be all the numbers inside. So we're going to do 2 times by 5. So 2 times 5 times 3. So 15 times by 2, which is 30. And then our lowest common multiple is essentially everything, well, inside. So we're going to do 5 times by 2, and then times by that 30, which is going to be 300. Lovely. Standard form. So standard form is always going to be, we're going to always write our standard form in a times by 10 to the power of n, where a must be a number between 1 and 10. So it has to either be equal to or more than 1, but it has to be less than 10. And n can be a positive or negative integer. Positive or negative integer. Okay, let's see this question here. So it says that we must express this number, so 47,400 in standard form. So remember, standard form is a times by 10 to the power of n, where a must be a number between 1 and 10, and n must be an integer. So what I like to do here is, so in order for this number here to be between 1 and 10, we can see that we have to put our decimal place next to the first 4. So we turn into 4.74 essentially. So because we are going to make a bigger number from 4.74, so 4.74 we're going to make that to a bigger number to get 47,400. That means we're going to times by a positive integer. When we're making a number bigger, well, yeah, when we are dealing with big numbers, our integer is going to be positive, but when we are dealing with smaller numbers, so like 0.000003, for instance, our power is going to be a negative number, a negative integer. So to know what our n is going to be, we need to work out how many times we have to move this decimal place to the right. So to get from this 4.74, and I'm going to put the 2 zeros here at the end, yeah. To get to 47,400, let's see, we're going to move it. So 1, 2, 3, 4. 4 times to the right. So that n is going to turn into 4. So our final answer is going to be 4.74 times 10 to the power of 4. Okay, now we've got this number here. So because we are dealing with small numbers, that means that when we do our a times 10 to the power of n, n is going to be a negative integer because we're going to move our decimal place to the left. But what I like to do first is to work out what this a is going to be. Because a needs to be between 1 and 10, that means the only way we can do that is by putting our decimal place next to the 6. So it'll be 6.789. Now we need to work out how many times we need to move our decimal place to the left by. So how many zeros are there? 1, 2, 3, 4, 5, 6, 7. Right? 1, 2, 3, 4, 5, 6, 7. So I'm just going to write 7 zeros to the left. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Very important to double check, guys. So now let's move our decimal place. So 1, 2, 3, 4, 5, 6, 7, 8. So we are going to have to move our decimal place 8 times to the left. Meaning that our number is going to be, in standard form, going to be 6.789 times 10 to the power of minus 8. Okay, this one here. Express this standard form in ordinary numbers. So now we're doing the other way round. So this 5 tells us how many times we're moving the decimal place. So this minus 5 here. So first we're going to move it 5 times. And because it's a negative integer, that tells us that we're going to get a small number. So we're going to be moving the decimal place to the left. So let's start off with 5.23. We need to move our decimal place 5 times to the left. So we go 1, 2, 3, 4, 5. Decimal point is here. Then we just add in our zeros. So our answer is going to be 0.00000523. And that is it. Okay, now we're going to look at multiplying and dividing standard form. When we multiply or divide standard forms, we put the front numbers together in one group and the powers of 10 to another group. Then we multiply or divide the front numbers and add the powers of 10s or subtract the powers of 10 in the other group, depending on whether we are dividing or multiplying the standard forms. So let's do an example. So here we have 2 times 10 to the power of 3 times by 6.75 times 10 to the power of 9. Okay, so what we do, so we group the front numbers together, so 2 times by 6.75, and then we group the powers of 10 together, 10 to the power of 3 times by 10 to the power of 9. So first, let's do the left-hand side first. We need to work out what 2 times 6.75 is, which is 13.5. And then to work out what this is, remember our index law. When we have numbers of the same base, we add the powers. So essentially what we're going to do 3 add 9, which is 12. So times 10 to the power of 12. And that is it. Similar thing with this one, we're dividing. So 2.4 times 10 to the power of minus 6. Divide by 9.6 times 10 to the power of negative 8. Again, we group our front numbers together, so 2.4 divided by 9.6. And then our 10 to the power of minus 6 divided by 10 to the power of minus 8. Let's do the left-hand side together. So 2.4 divided by 9.6. If this was a non-calculator exam, what we would do is, I like to write it as 2.4 over 9.6. And then what I would do here is I would multiply the top and bottom by 10 so that I can turn it into a whole number. So we get 24 over 96, and then I would simplify the fraction. So 24 and 96, off the bat, I know it's divisible by 24, but if we didn't know, we can see that, okay, these numbers are divisible by 2. So 24 divided by 2 is 12, and 96 divided by 2 is 48. Then we may see that, oh, okay, 48 is in the 12 times table, so we can divide that by 12. So 12 divided by 12 is 1, and 48 divided by 12 is 4. So we get a quarter. A quarter in decimals is 0.25. Okay, so 0.25 is our left-hand side, so that bit here. Now to work out what this one's going to be, when we have powers of the same base, we subtract the powers from each other. So essentially we're going to do, so our 10, we're going to do minus 6 minus 8. Because we've got two minuses, so two negatives makes a positive, so it will then turn into minus 6 plus 8. Minus 6 plus 8 is 2, so it will be 0.25 times 10 to the power of 2. But is that in standard form? No, it isn't, because if we remember, the A bit, so this bit to the left-hand side needs to be between it needs to be between 1 and 10, and 0.25 is way smaller than that. So what we are going to do then is we need to turn this 0.25 into 2.5. But if we're going to turn that into 2.5, that means that we'd have to just times by 10 to the power of 1, essentially. Because 0.25 times 10 to the power of 2, if we move the decimal place 2 times to the right, we get 25. If we want to start from 2.5 to get to 25, we only need to times by 10 once. Okay, now we're going to look at adding powers, or adding standard form, I mean. So when we add standard forms, there are two methods you can do it. So you can essentially turn these numbers into ordinary numbers, or, which I prefer anyway, is to essentially make them have the same powers to 10. So essentially what we're going to do is we're going to turn this 10 to the power of 3 to 10 to the power of 4. So let's look at 6.6 times 10 to the power of 3. If we want to turn that to the power of 4, that means that we need to make this 6.6 a little bit smaller. Well, one smaller, one decimal place smaller. So that means that will turn into 0.66 times 10 to the power of 4. Why? Because if we do 6.6 times 10 to the power of 3, the power of 3 means that we move the decimal place 3 times, and because it's a positive integer, we move the decimal place to the right. So it would be 1, 2, 3. So we get 6,600, right? If we start from 0.66, to get to that 6,600, we have to move the decimal place how many times? So 1, 2, 3, 4 units to the left. Meaning that if we want to times 10 to the power of 4 for this one here, we have to change this 6.6 to 0.66. Okay, So now that our powers of 10s are the same, we do kind of a similar thing to what we did for our adding and for our multiplying and dividing fractions. So what we're going to do is we're going to, did I say fractions? I meant standard forms. Don't know why I said that. So what we're going to do is essentially put the front numbers together, so the 9.8 and the 0.66, and we're going to add those two numbers together. So do 9.8 plus 0.66, and because the standard, the powers of 10 is the same, we're still going to keep it as it is, essentially. So then we just work out what 9.8 plus 0.66 is, which is 10.46 times 10 to the power of 4. But this is not in standard form because our number here to the left, that 10.46, needs to be between 1 and 10. And as 10.46 is above 10, it's not in standard form. So what we need to do is turn this into 1.046. And in order to do that, we have to times that by 10 to the power of 5. Okay, this one here. So now we've got this one. So we've got 4.2 times 10 to the power of 7 minus 6.1 times 10 to the power of 6. Similar thing, what we do, we're going to turn this power of 10 to the power of, power of 6 to the power of 7. So 6.1 times 10 to the power of 6, okay? If you want to turn that to the power of 7, that means that our 6.1 will have to turn into 0.61, essentially. Okay, so 0.61 times 10 to the power of 7. And then I add that one back in. Again, same thing that we do. So essentially we're going to do 4.2 subtract 0.61. And because they're both to the same 10 to the power of 7, we're going to keep that the same. So we're going to do 4.2 subtract 0.61, which we get as 3.59 times 10 to the power of 7. And is this in standard form? Let's see. Yes, because our number, our 3.59, is between 1 and 10. So it is already in standard form. Well done. Good. Lovely. And that is it for numbers. We have finally finished numbers, gone over the whole topic of numbers so far, which is excellent. Well done for all of you that managed to stick through it, and hopefully you found it helpful. Good job. Well done.